Hello, in this video we will look at relative position and relative motion. These are important concepts as they tell us how to relate observations made by different people. After all, we can have different observers looking at the same phenomenon and coming up with different results. For example, if you were standing on the ground and watched a train passing by, you might say that its speed was 60 miles per hour. However, someone else in a car traveling at 50 miles per hour in the same direction as the train would say that its speed was only 10 miles per hour. Neither of you would be wrong. And if both of you are correct, then there should be a way to relate your observations. This is what we will study in this video. Since physics works the same everywhere, we should be able to predict how different observers see the same phenomenon using the same laws. To start off, we will see how different observers, each with their own coordinate systems, describe the motion of a particle. Here is A with his axes. He is observing a particle P. He draws a position vector starting from his origin and pointing to P. He calls this the position of P with respect to A. Remember, P/A is read as P with respect to A. In other words, it is the appearance of P as seen by A. Now we introduce B, another observer, with his own origin and his own set of axes. For simplicity, we will make sure that this axis x prime is parallel to x and y prime is parallel to y. But in general, this need not be so. Here again is the position of P with respect to A, which remember points from the origin of A to the point P. And here is the position of B with respect to A, which points from A to B. Finally, we complete a little triangle by drawing the position of P with respect to B. We see that we can either go directly from A to P, or we can go from A to B and B to P. In terms of the vectors, that implies that r of P with respect to A is equal to r of P with respect to B plus r of B with respect to A. R of P with respect to A is equal to r of P with respect to B plus r of B with respect to A. Or, equivalently, we could rearrange this to say r of P with respect to B is the same as r of P with respect to A minus r of B with respect to A. Remember that the minus sign simply reverses the direction. So, to find the position of P with respect to B, one way of doing so is to find the position of P with respect to A and then subtract the position of B with respect to A. This makes sense if we look at the picture. To get the position of P with respect to B, we look at the position of P with respect to A, but we realize it's a bit too big, and we have to subtract the contribution of B with respect to A, leaving us with just P with respect to B. As we have seen earlier, we can write the relation between the vectors like this. The advantage of writing it like this is that we notice that the middle letters essentially cancel out. This gives us an easy way to remember how to write the relation. We see that P is on top over here and on top over here. B is on the bottom over here and on the bottom over here. And A essentially cancels out. So we realize that when expanding a given vector, we keep the positions of our given two the same. P stays on top, B stays on the bottom, and the middle letters have to cancel out. In order to do so, they have to be the same. Remember that. If we take this relation and then differentiate it with respect to time, we see that we find the velocity of p with respect to b is equal to the velocity of p with respect to a plus the velocity of a with respect to b. This was essentially what was happening in the train example. Let's look at a specific example. Observer A is standing on the side of the road. Observer B is moving with a velocity of negative 15 meters per second I hat with respect to A. They both agree on the direction of their axes. And they both observe a third person P driving on the road in the positive x direction. A measures P moving with a speed of 35 meters per second. What does B measure? Try using this equation with the information given to you. Remember, the velocities are vectors. Try using that all together and solve this problem. We will now look at the solution. We are given that the velocity of B with respect to A is negative 15 meters per second I hat. We also have that the velocity of P with respect to A is positive 35 meters per second I hat. We know that the velocity of P with respect to B will be the velocity of P with respect to A plus the velocity of A with respect to B. The first we know is 35 meters per second I hat, but the second is the velocity of A with respect to B, whereas we know the velocity of B with respect to A. However, the two are simply related. The velocity of A with respect to B is simply the negative of the velocity of B with respect to A. After all, if A sees B as moving forward, then B would see A as moving backward, and vice versa. In this case, A sees B as moving backward in the negative I hat direction, and so B would see A as moving forward in the positive I hat direction with a speed of 15 meters per second in the positive I hat direction. Putting this together, we see that P, as observed by B, is moving with a velocity of 50 meters per second I hat. Now let's think, does this make sense? Well, as far as A sees, P is moving in the positive x direction and B is moving in the negative x direction. We know from experience that if we are in a car and we see a car coming in the opposite direction, they look much faster compared to when we are standing on the ground and watching them. The same effect applies here. Take a moment to look over the example. The important points are the relation between the observers and the object, and the fact that the velocity of B with respect to A is the negative of the velocity of A with respect to B. And of course, always remember that velocity is a vector, and so the I hats, j hats, etc., and the signs matter a lot. Here is another problem. Take a moment to look at it and try and work it out. We will now solve the problem. In every relative motion problem, we need to identify three things: two different observers and the object that they're both looking at. In this case, the object is the basketball. There is one observer on the ground and another observer in the car. Splitting up the speed of 2 meters per second into its x and y components, we see that the velocity of the ball with respect to the ground is given by this expression, where we have simply taken the x and y components of the velocity. We get 1 meter per second from 2 meters per second times cosine 60 degrees, and this from 2 meters per second times sine of 60 degrees. Next, we realize that we are given information on the velocity of the car as seen by the observer on the ground. This is simply 2 meters per second I hat. Finally, we want the velocity of the basketball as seen by the observer in the car. How do these three velocities relate? We start with the easy stuff. We write the two V's, we put the slashes, and then we remember, if B is on top over here, it has to be on top over here. If C is below over here, it has to be below over here. And the middle letters have to cancel, so they should both be G. This is our relation. Putting it all together, we see that we have the velocity of the ball with respect to the ground, and then the velocity of the ground with respect to the car. And from the perspective of the passenger in the car, the ground is moving backward, which is why that becomes negative 2 meters per second I hat. From here we can go on, simplify, get the velocity of the ball with respect to the passenger in the car, and then finally its speed by taking the magnitude. Here is another problem. A river flows due south with a speed of 2 meters per second. You pilot a motorboat across the river. Your velocity relative to the water is 5 meters per second due east. The river is 500 meters wide. We are asked to answer the following questions. Take a moment and try and solve it by yourself first. Pause the video to give yourself some time to think it through. We will now discuss the answer. In this problem, our three objects are the boat, the river, and the ground. We start by setting up our coordinate axes. We assume that east is the x direction and north is the positive y direction. In that case, the velocity of the river with respect to the ground is 2 meters per second in the negative j hat direction, since it is flowing south. The velocity of u in the boat with respect to the river is 5 meters per second I hat, since you're moving east. We wish to find the velocity of the boat with respect to the ground. Once again, we start with the easy stuff. We write the two v's with the vectors. We draw the slashes, and then we remember if B is on top over here, and B will be on top over here. If G is below over here, then G will be below over here. In this case, the common letter that cancels out must be R. Plugging in the numbers, the calculation is straightforward. This is the velocity of the boat with respect to the ground. Let us keep this in mind and move on to the next part of the question. We are told the river is 500 meters wide, and we are asked how much time will it take to cross the river. The river is flowing south. To cross the river, we are moving in the east-west direction. So, the 500 meters wide refers to the distance in the east-west direction. To determine the time, all that matters is our motion in the east-west direction. Here is our velocity with respect to the ground, and we see that the component of the velocity in the east-west direction is 5 meters per second. So, finding the time, since there is no acceleration involved, we simply do distance divided by speed to get 500 divided by 5 to get 100 seconds. Now we move on to the next part of the question. Here we are asked, how far south of your starting point will your landing point on the opposite bank be? We are moving south because we are moving with the river. Once again, to find the distance moved, we use d is equal to vt since there is no acceleration. But this time we are concerned with the north-south component of the velocity, which, if you remember, had a speed of 2 meters per second. We drift for 100 seconds, and so we end up 200 meters south of our starting point. Here is a similar but different problem. In this case, the river, again, is flowing south with a speed of 2 meters per second. Our speed relative to the water is 5 meters per second, but the direction has not been specified. We want the boat to head due east with respect to the ground. In other words, we need to compensate for the flow of the river. We are asked how we should aim our boat's velocity with respect to the water in order to achieve a total motion with respect to the ground that is due east. Let us try and solve this problem. Once again, the three objects are the river, the boat, and the ground. Once again, we set up our axes and write the velocity of the river with respect to the ground. In this case, we know the speed of the boat with respect to the river, but since we don't know the direction, we can't write it in vector form. It seems we don't have enough information. But let's try and go ahead. Let's start with the relation between the three velocities. Since we're interested in the boat with respect to the ground, we end up with this relation. Since this is a vector equation, we can split it up into its components. In other words, VB with respect to Gx component is equal to VB with respect to R x component plus VR with respect to Gx component. The same applies for the y direction. How does this help? We know that we want the boat to head due east. In other words, if we look at the velocity of the boat with respect to the ground, it should have only an east, that is, an x component. But this implies that the y component must be 0. So we focus on this equation. Plugging in the numbers, we see that we have 0 equals the y component of the velocity of b with respect to r plus negative 2 meters per second. What does this tell us? This y component must be 2 meters per second. We note down that information. We see that the y component is 2 meters per second. We know that the overall magnitude, that is the speed of the boat with respect to the river, is 5 meters per second. And we know the relationship between the overall magnitude and the components. Putting all this together, we see that Vx, b with respect to r, is the square root of 5 squared minus 2 squared, which is square root of 21 meters per second. Since we want the boat to head east, we are taking the positive square root. We note down this information. Since we now have the x component, the y component, and the magnitude of this vector, we can calculate the angle. Using arctan, we find that the direction of the boat's velocity with respect to the river is 23.6 degrees north of east. This is how we should aim the boat with respect to the water in order to compensate for the river's flow, so that our total velocity of the boat with respect to the ground is exactly due east. We see that the y component of the boat's velocity with respect to the river cancels out the y component of the river's velocity with respect to the ground, so that the boat, as seen by the ground, moves only along the east-west direction. We are asked for the boat's velocity with respect to the ground. We start again by relating the three velocities. We are looking for the boat with respect to the ground. Plugging in the results that we have from the previous part, we see that the boat only has an x component to its velocity. That is, it is heading purely in the east direction with respect to the ground, which is what we want. We are asked how much time it will take us in this case to cross the 500-meter wide river. Again, the crossing is in the east-west direction. And so, we only need to concern ourselves with the east-west distance and the east-west velocity. Plugging in the numbers for the distance and the velocity with respect to the ground, we see that the time it takes is 109.1 seconds. Let us now return to the various equations for relative position and relative motion. We start with the equation for relative position and differentiate it once again. Get an equation for relative velocity. If we differentiate it one more time, we get a relation between accelerations. Now, here is a special case. If B is moving with a constant velocity with respect to A, then the acceleration of A with respect to B, or of B with respect to A, is 0. Thus, this relation that we had between accelerations simplifies to just this. What does this mean physically? It means that both B and A agree on what acceleration they observe for particle P. If we continue and multiply both sides by the mass of particle P, then they stay equal. However, we will soon see that mass times acceleration is the net force on an object. And so what we are saying is that the net force on P as observed by B is the same as the net force on P as observed by A. In other words, the two observers, though they may disagree on the position of P and they may disagree on the velocity of P, they will agree on the acceleration that P has and on the forces acting on P. This is an important concept since it allows us to define what we mean by an inertial frame. Once again, the two observers A and B, who are not accelerating with respect to each other, will agree on the forces acting on particle P. Conversely, we can see that if one of them is accelerating, let's say B is accelerating with respect to A, then they will disagree on the forces acting on particle P. That is the end of this video. I'll see you in the next.